Okay, we're here for Trig Identities Day 2. I cannot promise I'll get through this lesson without some barking dogs and or screaming kids in the background, but we're going to try our best. Essentially, all I'm going to do is walk through the examples that Mrs. Crowfoot has posted on her website and just provide some explanation that goes behind it. I'll work out the problems, that you see up there. And if you have any questions, of course, you'll contact one of us and let us know. So the first proof that you see in the Day 2 notes is this one right here, 1 plus 2 sine cos over sine plus cos quantity squared, and apparently all of that equals 1. Well, I probably am not going to be able to change that 1 very much on this side to make it look like this easily, but if I start simplifying what's on the left-hand side here, I'm going to work on that bottom, the denominator, sine plus cos quantity squared. Just make sure for something like that. I know you would never do this, but it is a common mistake where students distribute the square into there and make it sine squared plus cos squared. But if you actually do the FOIL out, or you do your box method, you're going to wind up getting a middle term, which I'll write down in a second. You get a sine squared for sure, but you're going to get sine cos plus another sine cos, which is a plus 2 sine cos. And you'll also get plus cosine squared. So I can see, where that 2 sine cos is on the top. So that's going to be nice that I'll be able to maybe cancel that out at some point. But I'm also going to have to cancel out that 1 plus, right? Well, based on what we talked about yesterday, there is hopefully an identity jumping off the page at you that sines cost $1. So sine squared plus cosine squared is 1, so you can actually change that denominator into exactly what the numerator says. Sine squared plus cosine squared is 1. Then you get the plus 2 sine cos that was left from the foiling of this. And again, if you need to justify that for yourself and work it off to the side, then certainly do that. But hey, something divided by itself is in fact 1. So therefore, that identity is true. There's another identity that is worked out in the notes, and it is cotangent theta over secant theta minus 1 equals cosine cubed theta plus cosine squared divided by sine cubed. And I'll tell you, when looking at the website, the work that it takes to simplify this one is definitely a little bit more challenging, and it requires a skill that, to be honest, you won't see used very often, but it is the most effective way of going about something like this. And if you look at the website, what happens in this example is if you multiply the top and bottom of the left side, oops, I wrote that wrong, minus 1. I got ahead of myself here, by the conjugate secant theta plus 1, that is a strategy you can use to try and simplify this fraction, right? So we've done examples in the past where we've multiplied something by its conjugate to simplify the denominator here. And let's see what the result is from doing this. So we're going to get at the top cotangent secant plus another cotangent. So I'm just distributing cotangent across the top. On the bottom, that conjugate pair, remember, you could really just do the first terms and the last terms multiplied. So secant times secant is secant squared minus 1. And then from here, I guess you'd have a few different options. What I'm going to do, and what I think a good strategy is in these identity proofs, is change everything into sine and cosine. Because everything in our trig world can be expressed in terms of sines and cosines. Right? We have the quotient identities, we have the reciprocal identities that we're going to wind up using here. So for example, instead of changing cotangent into 1 over tan, it's going to be more beneficial for us here to make that cosine over sine. Okay. And that's being multiplied by 1 over cos. Plus, this is cosine over sine over here. And on the denominator, we have 1 over cosine squared, and then that minus 1. So we've created a complex fraction by doing that, but everything at least is in terms of sines and cosines. And why might I have wanted to do that? Well, check out what's on the other side. A lot of sines and cosines. All right. Before I actually do anything else, I'm going to simplify this by crossing off those cosines. So really, this is just 1 over sine, isn't it? And since it has the same denominator as this, we can probably even express this as 1 plus cos all over sine. And the denominator is 1 over cos squared minus 1. So this is definitely a complex fraction. We've got fractions within fractions here. So when simplifying a complex fraction, there's a few ways to go about it, but I think the easiest thing is to determine the LCD and then multiply the top and the bottom by that LCD. The LCD, if I look at the denominators, we have a sine, we have a cosine squared there. The LCD is in fact sine times cosine squared. So we're going to multiply the top by that. We're going to multiply the bottom by that. And let's see what we have left when we do that step there. So we're going to get the sines to cancel up here. Cos squared would get distributed across, so we would get cos squared plus cosine cubed. That's kind of looking promising here. Okay. On the denominator, if I multiply this through, we're going to get the cos squareds to cancel, so we get sine minus sine times cos squared. Sorry if you can't see that. Okay. All right. So I see definitely that the numerator matches this numerator up here. So I know that's good, but I have to somehow get the bottom to say sine cubed. And if you're looking at the bottom, I'm hoping that you're seeing that we have a GCF of sine we can factor out. And when I do that, it leaves me with 1 minus cos squared. And that 1 minus cos squared, I'm hoping that rings a bell from yesterday. So 1 minus cos squared is a Pythagorean identity, which is equivalent to sine squared. Right? If sine squared plus cosine squared equals 1, then this actually would equal sine squared. So I'm running out of space here. I'm going to carry my work this way for a sec. Numerator's fine. But after factoring out that GCF of sine, we're left with 1 minus cos squared, which is sine squared, better known down there as sine cubed. Sine times sine squared would be sine cubed. And then we would have that cos cubed plus cos squared on the top. Okay, so carrying this all the way back up to the top where I started not too long ago, seems like a long time ago, but those two quantities are in fact equivalent. Definitely a much more challenging proof than some of the other proofs that you'll see for practice, but I hope that the process made sense as we walked through it there. By the way, when you're doing these for practice, you know, it seems much easier when you're hearing an explanation and when you're seeing the work done out. It's sometimes a little bit more challenging when you have to go about and try them on your own. So if you get stuck at a certain point in the process, take a picture, send it to your teacher. I promise they'll help you figure it out. All right, we're going to kind of actually change gears a little bit in today's lesson and talk about how to solve trig equations. All right, so let's see. And if the directions say to solve an equation and it's not proving an identity, you can cross the equal sign now. Okay, you can add something to both sides. You can divide both sides by something, right? You can do all those standards that we would use in a typical equation. So Unit 15 was all about solving equations, so I'm hoping that some of this logic is going to make a lot of sense to you, but all we're going to mix in today is now we're going to also see some examples where we have some identities that we'll throw in the mix. So for example, 4 sine x equals cosecant x. What identity is going to help you out here? Changing cosecant into 1 over sine x. Okay, so use that reciprocal identity, make that substitution. If you then multiply both sides by sine x, we get 4 sine squared is equal to, make sure you still have 1 on this side. So if 4 sine squared is equal to 1, you can then divide both sides by 4. Sine squared equals 1/4. Here's a step where I think a few of us missed on the last unit test that when you take the square root of both sides, you definitely have to write plus or minus, important part there, plus or minus a half, which is actually kind of nice, right? Square root of a fourth is a half, so we're going to get some really nice reference angle solutions here. Sorry, last triangle got a little bit away from me there. So if this is x, sine is positive and negative, you get all four quadrants, right? You get the bow tie picture here. The reference angle for this is pi over 6 or 30 degrees. I didn't give you any instructions here actually, but in this example, you would be solving over the interval 0 to 360. We'll do a couple in degrees and then we'll throw some radians in as well. So if the reference is 30 in quadrant 1, the answer is, here's my solutions. We get 30 degrees, quadrant 2, 180 minus that is 150. 180 plus is 210. 360 minus would be 330 for quadrant 4. So just a little bit of a thought process behind solving that equation in number 3. The fourth example in the notes is sine theta equals radical 3 cos theta. When you see a mix of sine and cos in the same equation, there's a few different things that I'll suggest doing. Since neither of these are squared, the only way to get this down into terms of one trig function is actually dividing both sides by cos would produce a new trig function on the left. Sine over cos is tan. It's a quotient identity. Cos over cos cancels out. So if tan theta equals radical 3, tan is positive, all-star trig class, quadrant 1 and 3. Tan is opposite over adjacent. Okay, reference here would be 60 degrees. So in quadrant 1, the answer is 60. And in quadrant 3, the answer would be 180 plus that, which is 240. Okay. Here's one that will also have sine and cos on it, but it's going to have a pretty different feel. 4 sine squared plus 4 cos is equal to 5. Okay. So if you have two different trig functions, there might be a few different strategies. You know, in this case, I was able to divide out one to make a new trig function, make the function tan here. I'm hoping you see that probably wouldn't be applicable in this specific example. So to solve for x in this case, what is going to be the best case scenario is replacing sine squared with something. So when you see a trig function squared, we have some other identities that we can use to help us with that. And if sine squared plus cosine squared equals 1, it comes to that Pythagorean identity. We should know that sine squared equals 1 minus cos squared. That's going to be a really helpful substitution. It's going to get me an equation all in terms of the trig function cosine. So we get 4 times 1 minus cos squared plus 4 cos x equals 5. Distribute that 4. And then once you do that, it's really all about rearranging this to get it into standard form, and hopefully it's factorable. So if I think about adding 4 cos squared to the other side, I like factoring with a lead coefficient that's positive. I would have to subtract 4 cos x over, subtract the 4 over here to get a positive 1 equals 0. And it turns out that this is factorable. It's going to be 2 cos x and 2 cosine x. If you need a dummy variable, go for it, with a -1 and -1. So the nice thing is that not only is it factorable, but you're going to get kind of the same solution repeated on both sides. Cos x equals a half. So what are the angles for which cosine of x would equal 1/2? Well, cos is positive in 1 and 4. Cos is adjacent over hypotenuse, so here's your triangle. If the reference angle here is 60 degrees across from that radical 3, your solutions are 60 in quadrant 1, 300 in quadrant 4. Okay, one more that I'm going to do with you, and then there are a couple of other questions in the notes that certainly you can use as a reference point if needed, but I think this should get you to a pretty good place with some mixed practice of solving equations and those identities we started with. So the last one that we have is 2 cos theta plus 1 equals secant theta. And for this last one, I'll solve it over the interval from 0 to 2 pi. So I'll throw some radians back in there. So we did one earlier where we had a sine and a cosecant. hopefully you're seeing the connection here that you can change secant to 1 over cos. Now this will have a little bit of a different feel compared to the third one that we did today, because I am going to multiply both sides by cos. And what that leaves me with is 2 cos squared plus cos. And on this side, we now just have 1. Okay. So before, what we had is we didn't have that middle cos term, right? I think we just had, something sine squared equals 1, so we were able to pretty easily solve from there. It's not that this one's that much more challenging, but if you have a quadratic, don't take out that GCF of cos. I mean, that's going to get me back to this step anyway, but you have to set it equal to 0. Once I set it equal to 0, then you can determine a factoring technique that would allow you to solve here, and it is factorable. Okay, so play around with the factoring here to get a positive cos in the middle. It's going to have to be a +1 there, a -1 here. So we get cos theta equals 1/2, and I believe we just did that in the last question. So we should be pretty good at the reference angle here of 60. Now the only difference is that this time we want the angles in radians. So 60 would be pi over 3. In quadrant 4, all the way around is 2 pi, which is 6 pi over 3. So 6 pi over 3 minus your reference is 5 pi over 3. For cos theta equals -1. If you try and draw, a picture of the triangles in quadrants 2 and 3 where cos is negative, you'll find that that doesn't actually make sense because this is a quadrantal angle. Okay, so cos theta equals -1 right here, midway through that cos cycle at an angle of pi, and those are your 3 solutions. That was the really quick day 2 there, guys. So if you have any questions or thoughts, send them our way, and we'll get back to you as soon as possible. All right, thanks for tuning in. Day 3 tomorrow is actually just some practice, so you can take a step back and hopefully make sure you're understanding the material here. Thanks, guys.